Whatever you think, Autumn. Are you okay where you are? Or?
Well, I have bad eyes, so
okay.
I might have to sit here. Oh,
but like, no spitballing or anything back there. So, just kidding.
I'm gonna make paper airplanes and throw them.
So we're going to pick up where we left off. Now, there's called Your Turn 4.33 if you guys got your notes. And actually it starts with this figure. So it goes something like this. I'm reading off it. We have an A and a B. A says, a recent government report states that the atmospheric levels of CO2 has increased since 1860. So we find 1860, and remember we have three different gases here. We have NO2 and methane, CH4 in parts per billion, and then the green is the CO2. So would you agree with that statement A, that the levels of CO2 have increased since 1860? Let's see, right, so the green?
Yes.
Okay, me too, you know. We have a couple of slides, one more slide coming up to show you CO2 levels that are actually back, hundreds of thousands of years. Of course, this one just starts at 1750. I think the significance of 1850 or so would be the Industrial Revolution. And the Industrial Revolution has relied upon fossil fuels, which fossil fuels actually are emitting CO2s. The next one, it says, a global warming skeptic states that the percent increase in CO2 again since 1957 has only been about half as great as the percent increase from 1860 to the present. So find 1957, okay, and he says that this increase from 57 to here has been half as great as from 1850 to the whole thing. What do you think? You think that's true? I think the skeptics needs to get glasses or something. So basically, if we draw a line here, it's not letting me draw, but if we draw a line here to look at this increase, to me, that statement's not right. But the question goes on to say, skeptics about anything, including CO2 emissions, what sort of effect could that have on policy if you get out potentially misinformation?
You're going to make around policies.
Yeah, you can make policies based upon misinformation.
Fake news.
What's that?
Fake news.
Fake news. It gets so confusing. Maybe you guys already know this, but our kids, I think in K through 12 now, are having classes about how to discern information that you get maybe from the internet or Facebook or whatever. So our kids are having to, with their eyes open, be able to, what's the word? Just be able to understand the sources and things like that.
Yeah, it came up on my news feed that Sylvester Stallone was dead, so I thought he was dead.
Oh. And it's not true?
It's not true.
Poor Sylvester. Oh my gosh, what are you going to do? So this actually then is about CO2 levels. Anytime you look at a graph, you should kind of get your bearings, what it's talking about. So we have CO2 levels against parts per million, which is greater than parts per billion, you told me. And this actually goes back thousands of years now, so 800,000 of years in the past. This zero would be like as in now, okay? So this is going back in time, CO2 levels. How do you think we got these CO2 levels clear back here? What one of the things we talked about on Wednesday?
Core sample.
Yeah, core sample data is a big one. Yep. The word there is 100 parts per million. So here's where, again, I don't mean to pick on skeptics, but skeptics will say that actually this idea of fluctuation in CO2 levels, and actually in the next slide you're going to see that the surface temperatures go up and down too, and they actually track pretty good with our CO2 levels. CO2 levels go up, temperatures go up. CO2 levels go down, temperatures go down. Skeptics will say that CO2 and global temperatures have been going up and down for a long time, But like this slide says, we actually, with the advent of burning fossil fuels with the Industrial Revolution, we have actually left the safe territory. Okay, so you're talking 300 parts per million was kind of the tops historically before the Industrial Revolution, and now we're up to, I told you, 400. What was it, 408 the other day? Parts per million in our parts per million carbon dioxide in our atmosphere. So this is the slide I was telling you. Looks like the word that's hidden is correlated. Correlated. Anytime in science or otherwise they say that two things correlate well, that means that if one goes up, the other goes up. If one goes down, the other goes down. So the correlation we're looking at here, we have two colors here. The red is the temperature, and the blue is the carbon dioxide concentration. So they, they call it noise if you kind of see the jags, okay? It's a little noisy, but generally speaking, yeah, I think it's there. So these, I have a couple of slides now, actually, from your textbook that says what we know and what might be true. So stating what we know. We know that CO2, when it's in the atmosphere, it actually acts as a blanket. And CO2 will trap otherwise outgoing energy from the Earth, and CO2 will contribute to an elevated temperature. Okay. We also know that CO2 has been cycled up and down over the last hundreds of thousands of years. We can get from our ice core samples. But we know that based on the last 100 years, CO2, sometimes they call it a hockey stick, where basically, even though there were jags, we have, this is the CO2 before the Industrial Revolution, and this is the CO2 after the Industrial Revolution. I think that's almost an Al Gore thing. It looks like a hockey stick if you kind of turn sideways. So CO2 has increased sharply in the last 100 years. And it's safe to say that even though there are natural sources of CO2, things that put CO2 in the atmosphere, that quick increase has been due to human activity, anthropogenic sources. We also know that the surface temperatures have increased. Taylor looks so relaxed back there in her big old chair. It's comfy. It looks comfy. These things we know. Now, these things, what might be true, may or may not be true. So it might be true to say that carbon dioxide and other gases then are responsible for the increase in temperature. We see an increase in temperature, we see an increase in greenhouse gases, but does one cause causation, right? Now this may or may also be true. The average global temperature will continue to rise as we continue to increase our emissions of CO2. The problem with our CO2 emissions is we're going to talk a little bit about kind of putting things in place to reduce our emissions as a human species. But so far as we can tell, when you look at graphs, there's no leveling out of CO2 emissions. It's, yeah. No. So on to part 6. Hopefully. And it looks like it's up the graphs. Tiny little graphs. So radiative forcings. You're going to see a list on this graph of things called about radiative forcings. Radiative means radiation, and in this case it means actually thermal radiation that the Earth is taking in or giving up. So radiative forcing. It's the balance that we know the Earth tends to, we talked about that. that the earth oozes energy and the earth takes in energy. We talk, okay. So I kind of tried to chunk up this graph because it's a really busy graph. If we look up here in the upper kind of line, it says well-mixed greenhouse gases. CO2, what's CH4? What compound is that? Methane. Yep, very good. Now, I like this graph, and there's definitely some graphs at the end of this chapter that are just packed full of information. The second column says resulting atmospheric drivers. So, in other words, methane can give these rise indirectly to CO2, H2O, O3 is ozone, and methane, of course, is the original. Now, the way you read this is, can you see along the x-axis down here? This 0 means that it's a net wash. In the positive area means that actually it's going to have a warming. In the negative, it's going to have a cooling effect, right? So you kind of see that with regard to warming, our CO2, when I show you everything, we're going to see that CO2 actually has the potential most warming effect, followed by collectively these guys. Okay? So the greatest warming effects are found for greenhouse gases of carbon dioxide, water, methane, and chlorofluorocarbons. So here are the halocarbons, chlorofluorocarbons, okay? And this, we talked the other, I think Billy raised this, the N2O, the NOx gases, okay, they are greenhouse gas. Now, check out this with the CFCs and the HCFCs. You see this right up here? It actually can potentially have a cooling effect. That's what that little green bar means. And that's ozone. They're color-coded. They're crazy. Now, the difference here between these gases and these gases down here, these actually, it says short-lived gases and aerosols. Short-lived versus well-mixed. Carbon monoxide, resulting atmospheric drivers, CO2, methane, and ozone. Okay, they contribute to global warming. VOCs. VOCs are volatile organic carbons. I'm not kind of drawing blank what NM is. Okay. Greatest cooling effects are found for aerosols. So here we go. So aerosols are right here, particulates. Can you almost kind of see where they would have a cooling effect? The particulates have a cooling effect during the daytime because they block some otherwise incoming solar radiation. So that's where that is. Okay. Cloud adjustment due to aerosols. So the deal is as we do things to our environment, it can have consequences to kind of the balance, and one of the things is the balance of weather. Clouds actually can block incoming solar radiation and have a cooling effect. Albedo, your book talks about this, that you guys experience albedo all the time, like during the summertime. If it's hot outside, are you going to wear a white or black shirt? White. You're going to wear a white shirt if it's hot outside. The thing about white is that it's very reflective. It has a high albedo. Okay, if you wear black, it's actually going to absorb energy. So we can actually here on Earth do some interesting things with regard to changing large structures or small structures that can either absorb solar radiation or reflect solar radiation, just like white shirts and black shirts. Okay. One of the things that I know they've toyed around with in different countries, different parts of the world, is change the color of your roof.
Or did they make like white roads? They'll whitewash the road.
Yeah, whitewash it to,
We wouldn't be able to do that here because we have such different, dramatic, right?
What's that?
We wouldn't really be able to change the roofs here because our temperature and climate thing changes such different from winter to.
Yeah, exactly. Some parts of the world, because we have the gamut. In the summer, our summers are hot and our winters are cold. But if you're near the equator, you might go ahead and try to have as high an albedo, most reflective as possible. Yeah. And if you're up at the polar region, go with dark colored roofs. This last one down here. So sometimes, and again, I don't mean to pick on skeptics, but sometimes people will say, well, the sun is a variable in all of this. The sun sometimes can send us a lot of solar radiation, sometimes not so much. The sun does go through cycles. It's like an 11-year cycle where you have lots of sunspots and then not so many and lots of sunspots. But those changes, notice that's where those changes are. Not very much, and have potentially what it's looking like balancing towards the global warming. So collectively, these are global warming. Over here, these are global cooling, which, by the way, sometimes skeptics, and they're right, will say back in the 70s, I want to say, actually scientists were saying our temperatures were getting cooler instead of warmer. So, anyway, this is kind of what we have going on. Now, just like the weather forecasters basically use fancy computers to know what the weather's going to be hopefully tomorrow. I get it wrong a lot of the times, but that's what they do. They stick in conditions now, and they're like, oh, so that means that they forecast through using models and computers. So we also do that with climate modeling. So you're going to kind of see some kind of long-term sort of modeling based upon what we know about the atmosphere, what we know how the atmosphere has responded before, and kind of looking forward. Climate modeling. So, now this isn't going forward at all. This is kind of more reflective. We have from 2010, which is when these were taken, I guess, back in 1910. Now we have 3 different colors here. Again, a very busy slide. Let's see. The pink is what the models would say using both natural and man-made forcings. The green would just be natural forcings, natural elements of the atmosphere. And then the solid line is what we observed, okay? So what we observed. So with regard to temperatures, and these are all temperatures, so we have, the first 2 are temperatures, degrees Celsius. This actually is oceanic energies, okay? So can you see where the green says if we just use only natural forcings, okay, well, the temperature would maybe go up a little bit. Maybe increase slightly, just Mother Nature, okay? But you can see that what it actually did is the black line, it actually increased significantly other than just based upon natural forces. And notice then it's pretty solid that pink, that forecasting based upon natural and man-made activities kind of goes well with the black line. So what your author's done is kind of break it up by like latitude. Remember, latitude is how far away you are from the equator. So down here in Antarctica, notice that its temperatures have increased according to the dotted line here. And you can see the green line was natural and the pink line is natural and man-made. Pacific, okay, kind of at this latitudes, you see these same trends where the one that fits it best is actually the modeling where you include both natural and man-made activity. So in science, a lot of times, we'll look at the data. This is one way to look at the data, I should say. So there is hope. The international or intergovernmental panel on climate control. They've been in the news here and there. They've put out their reports. So intergovernmental means worldwide, basically. In 2014, they agreed on several points. First, human influence on the Earth's climate is clear. The word is highest. So humans are changing our atmosphere. basically, based upon what we do. Secondly, what these scientists agreed on is that the way or the reason we're changing the composition of our atmosphere is kind of twofold, two punches. First is burning fossil fuels, and the other one is deforestation. And the last thing they agreed upon was that our footprint that humans are putting on the earth, our fingerprint or whatever, is actually going to result in warmer temperatures, and the impact we're making is long lasting. Doesn't mean it can't kind of turn around, but like I said, anytime I've seen CO2 emissions, the hockey stick, it's still going up. So it needs to be more deliberate, I think, than it is right now. What we're looking at here, I think this looks like the North Pole to me, because that kind of looks like, or is that, I don't have my globe, maybe that is, I didn't think Antarctica had, yeah, Arctic, not the Antarctic. So this is looking down at the North Pole. The dotted line there is a region that used to be, have ice sheets on it. Here, according to when your textbook wrote this, it's looking like each year, or excuse me, each decade, we're losing about 9% of our sea ice. So the sea ice is thinning, okay? Thinning or melting. Now, a minute ago, you guys told me that if it's sunny outside and I don't want to be hot, I'm going to wear a white shirt. Well, the thing about ice sheets is ice sheets are generally white. So the problem with decreasing your ice sheet is basically what you replace it with is a black shirt. You replace it with something that's going to have a low albedo. It's going to absorb energy. And in climate, or yeah, I guess in climate more than weather, in climate we call this a positive feedback mechanism. It simply means that with higher temperatures, we're basically going to shrink our ice sheets, which is going to give us a lower albedo, less reflectivity. It means that we're going to increase our temperatures, and it's going to just keep kind of feeding on itself. Positive feedbacks does not mean a positive thing happens. It just means that it keeps doing what it's doing. Looks like I hid the word salinity in this, and actually I kind of chuckle because I think I mentioned the movie The Day After Tomorrow in here, and the premise for the movie The Day After Tomorrow, although it's a crazy movie, it is totally strange, but it said actually that what caused the crazy weather was this melting of glacial ice, and as it melts, then it changes the saltiness of the water, and changing the saltiness of the water, if you've heard of you watch Finding Nemo, they talk about those water, you can do the jet stream in the water and stuff like that. So it changing the salinity changed the density, which changed the movement of circulation of water. So bottom line. So I brought this one in. It wasn't originally in the author's PowerPoint slides, but I can kind of see why, because it's very small. Let's see what we think. So we're talking about risks and how to hopefully reduce those risks. So they kind of fall into these three categories. We have physical systems, glacier and snow, rivers and lakes, coastal erosions. Then we have biological systems, terrestrial ecosystems, wildlife, marine ecosystems. And then over here we have human and managed systems. And it says food production, livelihoods, health, and or economics. So starting up here, we have along the x-axis, we have risk level, low, medium, and high. Okay, and you can kind of see with regard to risk and present, what we've got kind of low to medium, near term 2030 to 2040. The bar gets a little bit over medium to very high. Okay. 2080 to 2100, which you're like, who's going to be around here? I won't then, but somebody will be. We increase our risk. Over here, and then each box is a different category. So with regard to oceans, you can see cute little fishy thing, right? With regard to fish and people, you can see how our oceans will be affected. I guess it is kind of a hard thing to read. Small islands, you know, melting glacial ice, rising ocean levels. North America, with regard to how they will be impacted, increased damage from wildfires. So this is us. Heat-related human mortality, increased damages from rivers and coastal urban floods. Do you hear like DC right now, or along the East Coast, it's having flooding and just crazy weather.
Did it? And we watched it say every full moon there's a flood in Miami.
Yeah. One of the articles, or I was listening on TV, it said, and the thing about the full moon is the moon acts as a gravitational pull to oceans and stuff, so tides are higher with full moon, and actually new moon too, but yeah. It's like, oh.
How would they, so there's a flood right now.
Right now they were having heavy rainfall, and plus, like you said, the moon's phase right now, and of course,
they get to full moon.
Yeah.
Sometimes.
So they kind of work together, yeah. Several years ago, Hurricane Sandy happened during not only just a full moon, but it was like a super moon. And super moon means it's full and it's also close because the moon's distance between the Earth and the moon kind of varies. And so Hurricane Sandy was really bad with regard to the timing and the lunar phase. Polar regions, how are they going to be hit? Central and South America, Europe, Africa, Asia, and Australia. Just kind of eyeballing these, and actually, I think now that I'm looking at it, don't you think too, that up here in the upper right-hand corner where they have present, near-term, long-term, okay, actually this is kind of a key for all of these because the four lines, each of the four lines kind of go with that, I think. Very busy.
I think it said in the book that, like you talked about sea level rising, a bigger factor than melting sea ice was like the warmer water. Yeah,
Okay. Thermal expansion.
Is that right?
Yeah, thanks for, yeah, you're right. And actually that was a question, I think maybe the person who was going to be over, it wasn't over EPA, but dealing with something, was asked about this idea of water. When you heat liquid water up, it has a larger volume. And exactly what Autumn was saying, as our temperatures increase in the Earth's atmosphere, there's a lag between taking that temperature and then actually, because water's pretty stubborn to heat up, to heating up our oceans. So there's a lag, but as those oceans heat up, they're going to actually, the liquid water will occupy more and more volume, which will then increase our sea levels. So, yeah, it's not good. So, I mean, in that sense, we're just kind of, even if tomorrow we shut off the valve somehow of our CO2 emissions, we'd still be kind of fighting some of this for a while. So one of the other things I added from what your author did was I took screenshots, basically this. So remember, the IPCC is that intergovernmental group of scientists across the world that came together to come to some conclusions. And so it's kind of broken up into unlikely, likely, and very likely, and it kind of goes up. So this is the bottom of the table, actually. So, and I didn't quite understand this unlikely, so I really didn't. But what things are likely according to these scientists, and none of these sound very good. Anthropogenic, remember that's man-made elements. have made a significant contribution to our increasing temperatures. You can kind of read this. So those are likely, very likely look like this. Okay. Just pick the second one. Very likely, since the mid-20th century, the number of cold days and nights has decreased. The number of warm days and nights has increased on a global scale. Now, again, you guys told me that climate is long-term and weather is day-to-day. So one of the things, and it may drive you nuts too, is for, go both ways actually. We have a really hot day and people say, oh, that's global warming. No, not necessarily. If we have a really cold day, then of course the people on the doubters, really cold day, they're like, oh, so much for global warming. It's not. But anyway, so the day-to-day weather is not the deal. It's the long term. Like this is saying, since the mid-20th century. Remember the 20th century is like the 1900s. Why did they do that? So anyway. So what's very likely to occur is that heat waves will be more frequent and longer duration, extreme precipitation events. Okay, now, I don't know if this is going to say it, but actually scientists, I think, are reluctant to say with regard to hurricane activities. This is not necessarily hurricane activity.
I think that's got more to do with the water temperature.
Yeah. But one factor of hurricanes is sea surface temperatures. But is that what you said?
Yeah.
Yeah. So, yep. So virtually certain and extremely likely. Pick the fourth one up there under virtually certain. Global mean sea level temperatures, like I was saying, will continue to rise. And so as the temperatures rise, like you were saying, often the water swells. And our little islands don't go out and buy land on the little islands. Because, it's not houseboat. Yeah. You guys probably don't remember Gilligan's Island, but there was an episode of Gilligan's Island where, they're shipwrecked on an island. It's so funny. Anyway, so he kept going out and he was catching lobsters or something, and so he had stick, and each time he'd go out, it'd be like the water would be higher up on the stick, and they thought that their whole island was gonna be taken over by water, but I think he did something stupid. Anyway, Gilligan, what are you gonna do? So this is a photo from your textbook, and 1992 is the year, and this is marking where the glacier was, and the glacier has retreated back that far. So it's just one of
That's a long ways for
just
that many years.
Mm-hmm. And this actually, it's and we could do some math, and I'm not sure we'll necessarily do this math, but per person, per capita, does per capita mean per person? Okay. So per person, the size of the foot and kind of the number underneath it showed relative sort of our carbon, I think this might just be our carbon footprint, or I don't know if it's our environmental impact of the making. But per person, this is what we're looking at in the US. This is global average. And how did China get? I don't know, because so many people living here.
They have a lot of alternative energies.
What's that?
They have a lot of alternative energies.
Alternative energies?
But we're the worst, right?
We are the worst.
Yes.
We're the biggest foot. Yeah. And there are neat activities you can do, I know, online. There are things you can kind of plug in what you do in a day's time, and it will tell you what your global footprint is. Okay, so one of the things, I'm biased because kind of my background is in the field of science, but when science comes out and tells you something, when worldwide a set of scientists come out and like the IPCC or whatever that was, tells you something, scientists, how do I say? Well, a few things. They have followed the scientific method and they have data to back up what they say. I know that there are scientists on both sides, but I don't know what I'm trying to say. But anyway. So we've been working on it. Kyoto Protocol 1997 established goals that would hopefully stabilize and reduce greenhouse gases. But like I said, I don't think we're seeing it yet, right? What are greenhouse gases? Well, we talked about CO2, methane, NO, HFCs, PFCs. Okay. Now, the last slide I have actually talks about this idea of being able to trade your emissions. Okay, I'll show you what that looks like. So here on the left, it's like basically across the board, every plant, so we have a plant A and a plant B, has to go ahead and reduce their emissions by 30%. So here's the deal though, if you let them, the title here says a flexible cap and trade approach. I'm thinking, I don't know, maybe you guys know more about this, if both plant A and B have to be owned by the same person? No, not necessarily. They can be different people. Because what you see here is that plant A has actually paid plant B, so it doesn't have to have the reduction that, it doesn't have to have that 30% reduction. So plant A pays. And so you can see that instead of 420 tons, it's still back up at 500. So it went from 600 to 500 instead of 600 to 420. But in doing this payment, it got a permit from this guy over here. So this guy got money, okay, and he went ahead and reduced, instead of reducing it, what is that, 120? It reduced it 200, okay? So plant B got money to do more of a reduction from plant A, basically. So kind of the net down here, notice that the reduction is still the same. Kind of just move the emission around, okay? But at a savings of money. Instead of the $12,000 it would cost to accomplish those reductions to 300 tons, it only costs $9,000. To me, when I read this, don't you too, as I'm thinking about this, plant B must have had maybe an easier venue, an easier path to reducing it than plant A. Maybe plant A is an older plant. Plant B is that kind of more the modern sort of things, but they were able to reduce it more easily. So, money. Okay. So I know it seems like, are you serious, Mrs. Snipes? Usually you just like creep through the material. But I want to go ahead and start on chapter 5. Happy Friday. So homework for chapter 4 is due Monday. Is that right? No? Yeah. Okay. And then your unit exam is going to cover chapters 3, 4, and just the first parts of chapter 5. And then your unit exam will be open Tuesday through the following Monday. Okay. That's what I thought too. So we're going to start out with the video. I feel like we're kind of switching gears a little bit. Among things we're going to talk about in this chapter, we're going to focus on fuels. Actually, it might seem very familiar to kind of the lab that you guys did on Tuesday. You guys saw when you burn fuels, they're not all equal, are they? We're going to kind of talk about that. Talk about how we can get electricity out of different ways. Talk about biofuels. Next Tuesday, you guys are going to make biofuels in the lab. So that's the plan. Let's take a look at this intro video. Actually, I'm going to throw it back at you. Just kind of have some questions. I know we haven't talked about fuels, but I bet you guys got some ideas. And let's go around the room and see what we can do. So, Autumn, what do you think?
Ooh,
What properties would make a fuel good or bad? Or give me one property.
Combustible?
If it's combustible, I like that. Okay, let's go back to you, Glenna. What fuels would make, a fuel good? I mean, what would make it good? What's that?
I said, I haven't got, the rest I got.
How about your pocketbook? It's an
Like
old time way of saying, yeah.
Being cheaper.
Being cheaper. I'm thinking. How about something else that's good?
I would say efficiency.
Efficiency? Yeah. Very good. Billy?
Supply.
Supply, if it's available. Talking like an economic person. Okay, Autumn, what would make it bad?
Like a lot of emissions.
A lot of emissions, yeah, a lot of pollution. Okay, this might be harder. What do you think, Autumn? You just take the opposite of all the other things we said.
Well, like she said earlier, like the combustion of it, it's not combustible at all.
Yeah, oh yeah, if it doesn't burn, right.
If it's not efficient.
If it's not efficient, really?
Opposite.
If it's, there's very much of it.
If it's very limited supply. Yeah, it'd be silly to make a technology that like used gold to burn. We're like, really? What have you done with that? Yeah. Let's see what other, let's skip to. So what do you think with 3, Autumn? Why do you think we've shifted away from using wood? Historically, we used wood. Why did we switch to using coal and then other fossil fuels?
Wood, I mean, we're cutting down trees.
Right?
So coal is maybe more plentiful, and then, I don't know.
Yeah, she said, wood, you're cutting down trees, and coal seemed like they'd be more plentiful.
And then you're getting natural gas when you're extracting oil anyway, so you might as well use that.
Mm-hmm. Are you guys struck, because my husband and I are, that, I mean, a gallon of gas, you're like, oh, well, the price has gone up, but what is it now? 2.5? I was correct. Is it 3.5? How much is gas? $2.20 a gallon? Yeah. I mean, that's still pretty cheap for a gallon of gas to think of what they did to get that gallon of gas. I feel like, no.
That's expensive.
I think, and I'd have to look, I think if you go into other countries, I
It's a
think
lot higher.
it's a lot higher.
It's a lot higher.
Yeah.
Other parts of the world too.
Mhm.
But they don't drive as much, I don't feel like, as
Yeah.
Americans.
We are
do.
consumers. Yeah. I think they share rights more than we do. And they do mass transit more than we do. Yep. It's interesting, though. Yeah. Well, and last Tuesday's lab, you guys burned the stuff that was in your little, your liquid, right, through a wick. And in order for something to burn, you have to have the fuel. Okay, it's a chemical reaction, though. Combustion is a chemical reaction. So the liquid was the fuel. What was it combining with? What's the oxidizer? For last Tuesday's lab, when you were burning your lamps. That would be the heat source. The match would be the heat source. I was after just oxygen, actually. Yeah. But in order for it to keep burning, we needed the wick too, didn't we? To kind of allow a spot where the oxygen from the room could go ahead and combine with our liquid. Yep, this would be the oxygen from the room. This would be the fuel from your little thing. Yeah, the heat would be the match. So, most fuels are hydrocarbons, and we talked a little bit about kind of naming compounds. And I like the word hydrocarbons because in the name for hydrocarbons, like, I don't know what it is. Yes, you do. Hydrogen and carbon, hydrocarbons. Okay. Now, granted that there are definitely compounds out there that contain hydrogen, carbon, and oxygen, and we don't call those hydrocarbons. So when we look at how carbon bonds with other things, when it's a hydrocarbon, oftentimes it is bonding with 4 other atoms. It's not bonding with 4 other atoms necessarily. It forms 4 bonds. Some cases it's a double bond, in some cases it's a single bond. So I have some examples to show you over here, and each of these figures of a molecule, the molecule it represents is C4H10. 4 carbons and 10 hydrogens in all of these representations. Now, how do we represent a molecule? We kind of got Lewis structures. They'll kind of look like a Lewis structure, some of them. But we use terms like structural formulas, condensed structural formulas. Okay, so let's see what they look like. So C4H10. 4 carbons, and this is what we've talked about prefixes. But means 4, and ANE means an alkane, which means they're all single bonds. So yep, this is this chain of carbons, and we have 10 hydrogens like that. We could draw it like this, okay, where the difference between these two is we're kind of trying to show a little bit better. Those carbons aren't on a straight line. The carbons zigzag, because if you look around each carbon atom, it's got that tetrahedral shape. So it kind of does do that sort of thing. We could do it this way, which we're kind of showing the kind of the zigzag of the 4 carbons. And we kind of show clustered around each carbon what they've got going on. Around the end carbons, we have 3 hydrogens. Around the middle carbons, we have 2 hydrogens. You guys have this right. Now, this one, you're like, are you serious? It's almost like the chemist got lazy. But anytime you see this sort of formula, think at the ends we have a carbon, 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 carbon. So we have a carbon at the ends, we have a carbon where each of the vertex of the lines are. And then you're just supposed to know that, well, if I don't have anything else written around it, I must have hydrogens scattered from them, so it's connecting with 4 different things. So that means this guy has 3 hydrogens, this guy has 2 hydrogens, 2, and this guy's got 3 hydrogens. And then this is kind of a nice way to do it, I think. Where you show, again, we have the 2 ends have 3 hydrogens, so CH3, CH3, and we have CH2, CH2 in the middle. To me, these are kind of similar. Well, that's a good place to stop. Then we'll hit it again on Monday, before spring break. Woo!